Hey guys, today we're going to be using the definition of the derivative to find derivatives of various functions. Before we begin our first problem, I want to go over some problem solving strategies. Our goal is to manipulate the function or expression in a way such that we could remove the h in the denominator. This is because if we plug in h equals 0 right away into the limit, we would have a 0 in the denominator as shown by the picture. By getting rid of the h, we could then plug in h equals 0 without needing to do any more work. You will see that in 4 out of the 5 example problems, we would end up factoring the h in the numerator, causing it to cancel with the denominator. We can manipulate our function using the same techniques that we've learned for limits. For instance, for radical functions, a common sequence is to multiply the numerator and denominator by a conjugate of the numerator, and then to use the difference of squares to get rid of the radicals, since this would result in squared terms allowing us to cancel out the radicals. For rational functions, you may have fractions inside of fractions. This could be done by multiplying the numerator and denominator by the common denominator. Generally, you want to distribute binomials and cancel out terms, allowing you to factor out h more easily. And finally, once there's no h in the denominator or anything that causes the denominator to be 0, when you substitute 0 for h, then you could plug in h equals 0 and simplify your expression to get your final answer. Our first problem will be finding a derivative of a polynomial. The first step is to just use the definition and to plug in our function f of x. We're just following what the definition says, and we're composing x plus h into our function, and then subtracting f of x from it and dividing by h. So we end up with 3 times x plus h cubed minus 5 times x plus h squared plus 7 times x plus h plus 4 minus quantity 3x cubed minus 5x squared plus 7x plus 4 all over h. Then I see that there are a lot of x plus h cubed and squared terms that are there. If we expand the binomials and distribute everything, the terms that don't contain an h might cancel out. So as you can see, we're expanding everything. X plus h cubed becomes x cubed plus 3x squared h plus 3x squared plus h cubed. Same thing with x plus h squared and x plus h. And notice how all the terms that don't contain an h cancel out, like the 3x cubed and the negative 3x cubed, the negative 5x squared and the 5x squared, 7x, 7, and 4 and 4. Then we can go and combine like terms, and notice that how all the terms contain an h now. This is the perfect time to factor out the h, and we could divide by it. Now here, there's no denominator, so therefore we can plug in h equals 0 and simplify our final answer. Once we do that, you can see the green zeros that are there that remove everything, and we just end up with 9x squared minus 10x plus 7. By expanding the binomial, the h in the denominator was gone, similar to what we did when we found the derivative of x squared, and this approach is common for all types of polynomials. Let's now look at what happens when we're dealing with some other types of functions. For instance, what would we do if we have a radical function f of x equals square root of x squared minus 1? Once again, we would begin with the definition of the derivative and plug in f of x equals square root of x squared minus 1 into our definition. I observe that in the numerator, the x plus h terms are trapped inside the radical, so I'm going to multiply the numerator and denominator by the conjugate of the numerator. In the last video, I told that techniques similar to rationalizing the denominator would be used, but it's actually more like rationalizing the numerator instead, since we want to manipulate the numerator such that we could factor an h term from it. So therefore, the conjugate would be square root of x plus h squared minus 1 plus square root of x squared minus 1. When we multiply this, notice that in the numerator, we have something that resembles a minus b times a plus b with the two radicals, square root x plus h squared minus 1 and square root of x squared minus 1. Therefore, we would have a squared minus b squared by the difference of squares formula. Notice how this helps eradicate the radicals in the numerator, freeing up the x plus h terms, allowing them to be combined, and we could eventually factor out the h. So now we end up with square root of x plus h squared minus 1 squared minus square root of x squared minus 1 squared. So the square roots are cancelled out, and we end up with x plus h squared minus 1 minus quantity x squared minus 1. Now I see that the x plus h term is squared, so therefore we can expand the binomial. So we have x squared plus 2xh plus h squared minus 1 minus quantity x squared minus 1. Once we combine like terms in the numerator, we're left with 2xh plus h squared. Once again, just as before, we could factor out the h and cancel it with the h that's already in the denominator from the beginning. Notice that the denominator still contains radicals, which is totally fine. Plugging in h equals 0 does not make the denominator equal to 0. The only thing that made the denominator 0 was the isolated h term, which we got rid of. Do not try and make it more complicated for yourself by trying and clearing up the radicals in the denominator. As soon as you could, plug in h equals 0. When we do so, we could combine the square root of x squared minus 1 terms, which are in the denominator, and we end up with 2 times square root of x squared minus 1 in the denominator, and we end up with 2x in the numerator, cancel out the 2's. Our final answer, f prime of x, is x over square root of x squared minus 1. Therefore, with radicals, the general strategy is that you want to multiply the numerator and denominator by the conjugate of the numerator, and notice that we're using multiple techniques. We're first conjugating the numerator, and then we're expanding the binomial, similar to the previous example. It is common for one technique to lead to another, similar to this example. You just gotta look at the expression and see what you have to work with. Once the radicals were gone, we had an x plus h squared, so naturally we knew we should expand the binomial. So what would we do if we have a rational function such as f of x equals x squared plus 3 over x minus 4? We're going to start with the definition of the derivative, and we're going to plug in f of x. And when I do that, I see two fractions inside in the numerator of a larger fraction. So we could eliminate the two smaller fractions by multiplying them by a common denominator of two fractions, which is x minus 4 times x plus h minus 4. From there, we have x plus h squared plus 3 times x minus 4 minus x squared plus 3 times x minus 4 plus h. If you want, you could FOIL out all the terms completely, which are there in the fraction. However, that would require a lot of work dealing with trinomials and binomials and just dealing with a lot of terms. If you look at the orange brackets, I'm instead just going to treat x minus 4 as a single term, and I'm going to distribute the x squared plus 3 term to just x minus 4 and h. From there, notice that 2 out of the 3 terms in the numerator contain x minus 4, as highlighted. Therefore, we could factor out the x minus 4 from the 2 terms in the numerator, and all we have to deal with now is the expression in the bracket, which is far easier than dealing with trinomials. Expanding and combining the like terms in the bracket, we could cancel out the x squared and 3 as shown in the purple, while the right side of the numerator, negative h times x squared plus 3, is left alone. We could then combine the like terms inside our expression to get 2xh plus h squared. So we have x minus 4 times 2xh plus h squared minus h times x squared plus 3. Now notice how all the terms in the numerator have a h. In the left portion of the numerator, both the 2xh and h squared terms have a h which we could factor out, while for the right side of the numerator, the h multiplies x squared plus 3. We could therefore pull out the h from both sides of the numerator as shown. The 2xh plus h squared becomes 2x plus h, and on the right side of the numerator, we're left with x squared plus 3. The h's could then be cancelled out with the denominator. With nothing in the denominator being 0 when h equals 0 could safely be plugged in. The x minus 4 terms in the denominator could be combined to get x minus 4 squared, and the numerator could be simplified to x squared minus 8x minus 3 by combining like terms. I understand it may have been a bit different the way I distributed the x squared plus 3 term. If you distributed everything and combined everything, that would have also worked, don't worry about it. However, notice that you're beginning to see a pattern when doing these problems. All you're doing when you're solving these types of problems is just following a bunch of steps. Based on what type of function you have, whether it's rational, radical, polynomial, you know what the first step should be. From there, after completing the first step, you see what you have to work with. If you have binomials raised to a degree, most probably you should expand it. If you have another radical in the numerator, you should multiply by its conjugate. And your goal ultimately is to factorial h in the numerator, such that you could cancel it out with the denominator. As long as you know what type of functions you're dealing with and the concepts from pre-calculus and algebra, this ends up being nothing but a mechanical process that you're doing with a series of steps. You know how to do all of this. You know how to combine like terms. You know how to go multiply by the conjugate. You know how to find the common denominator. We just need to apply it through finding the derivative. And this is what we're going to be doing in the next problem. We're going to be finding the derivative of f of x equals 1 over x times square root of 3x plus 8. Notice that both it's a rational and a radical function. So just as before, we're going to start with the definition of the derivative, and we're going to plug in f of x. So the first thing I see is I see two fractions inside of a larger fraction, so we need to multiply by the common denominator, just as before. So we're going to multiply by x times x plus h plus square root of 3x plus h times square root of 3x plus h plus 8. So from there we do that. We got rid of the fractions, but we still see that there are radicals there that are blocking the x plus h terms. So we need to multiply by its conjugate of the numerator, which is x times square root of 3x plus 8 plus x plus h times square root of 3 times x plus h plus 8. We multiply that both to the numerator and denominator, and just as before, we have a minus b times a plus b, a squared minus b squared, and we end up with x times square root of 3x plus 8, all of that squared, minus x plus h times square root of 3x plus h plus 8, all of that squared. So from there we cancel out square roots on the numerator, and now what do we see? We see that x plus h is squared, so therefore we need to expand the binomial. So we go ahead and do that. Now this, we can't escape these two trinomials, we gotta go expand them. But after we go expand them, we see that the 3x cubed terms cancel, the 8x squared terms cancel, and the other terms, you could see how I highlighted everything else. For instance, the negative 3x squared h and the negative 6x squared h, they combine to get negative 9x squared h. Same thing, you get negative 6xh squared minus 3xh squared, you get negative 9xh squared. Similar with the 16xh, and then you have negative 3h cubed minus 8h squared. Those last three terms could not be combined in the purple and blue. You can see how I'm trying to keep track of my terms, because it's a lot. You have these different combinations of x's and h's, and you need to make sure that you're keeping track of all your terms, and I did that through highlighting. So notice that once we simplify everything, we end up with, in the numerator, negative 9x squared h minus 9xh squared minus 16xh minus 3h cubed minus 8h squared. And what's going on in the denominator might seem like a lot, and it is, because you have all these square roots and everything there. However, we need to focus on what we need to do. All we need to do is factor out the h in the numerator, divide it with the h in the denominator, and then we could go and plug in h equals 0. So we could factor out and cancel out the h's, and we could go plug in h equals 0. And notice that when I plug in h equals 0, there's nothing that causes the denominator to equal 0. So you end up with negative 9x squared minus 16x in the numerator. So there's a lot of stuff we can do to simplify it. First of all, we could factor out x in the numerator. So therefore we end up with x times negative 9x minus 16. Another thing we could do, notice that in the denominator we have in the brackets x times square root of 3x plus 8 plus x times square root of 3x plus 8. We could go and simplify that to 2x times square root of 3x plus 8. Notice that we could also cancel out an x in the numerator and an x in the denominator. We have x times negative 9x minus 16 over x squared, which we got from multiplying x by x in the denominator. So when we cancel all that out, we're just left with an x in the denominator. So from there, we have negative 9x minus 16 over x times 3x plus 8 times 2x times square root of 3x plus 8. Notice that 3x plus 8 times square root of 3x plus 8 is just 3x plus 8 to the 3 halves. And notice that we have x times x is equal to 2x squared. So we end up with negative 9x plus 16 times divided by 2x squared times 3x plus 8 raised to the 3 halves power. So notice that we were just following a series of steps once again, and it didn't matter, there's a lot of stuff going down the denominator, a lot of stuff that was there everywhere, but we just focused on what we need to do. It doesn't matter whether you have x squared, x to the 1/2, 1 over x squared, x cubed, it doesn't matter. We just need to follow a series of steps, which is what we did during these 4 examples. And we need to work with what we're given, such that we could use our problem-solving strategies to end up with a final answer. So for our final problem, we need to find the derivative of sine of x. And this is going to be very different. The same strategies we've been doing is going to apply to this problem, but it's going to apply it in a different way. So first thing, just as always, we plug in sine of x into our definition. So we have sine of x plus h minus sine of x over h, and we're taking the limit as h goes to 0. Now all the strategies we've learned earlier about rational, radical, polynomial functions, that's all gone. It's a different type of function we're dealing with. But we need to work with what we're given with. What do we need to do? We need to get rid of the h in the denominator, and then we need to plug in h equals 0 such that we could end up with our final answer. Working with sine of x plus h, the huge chunk, is not going to be that helpful because we want some way to factor the h out. So how could we do that? Well, trig functions such as sine of x, they tend to be very malleable. You could change it very much. So what you could do is you could actually use this angle sum identity. So you end up with sine of x times cosine of h plus cosine of x times sine of h minus sine of x all over h. So notice now that 2 out of the 3 terms contain sine of x. So we could factor out sine of x from those 2 terms, and we end up with limit as h approaches 0 of sine of x times cosine of h minus 1 plus cosine of x times sine of h all over h. So are you starting to see something familiar now? Notice that you're starting to see sine of h over h. So that seems very familiar because we know that as h approaches 0, sine of h over h approaches 1 from pre-calculus. So therefore we could apply that. So we could start by breaking up this huge fraction that's there to get sine of x times cosine of h minus 1 over h plus cosine of x times sine of h over h. And if we break up that fraction, that means we have 2 different limits now. So we have the limit as h approaches 0 of sine of x times cosine of h minus 1 over h, and the limit as h approaches 0 of cosine of x times sine of h over h. Now notice that since it's the limit as h approaches 0, sine of x could be factored out. Similarly, cosine of x could also be factored out. And we know that the limit as h approaches 0 of cosine of h minus 1 over h is 0, and the limit as h approaches 0 of sine of h over h is 1. We simplify, we end up with f prime of x equals sine of x times 0 plus cosine of x times 1, and we end up with our final answer of being cosine of x. The derivative of sine of x is cosine of x. How nice is that? Notice that even though we're dealing with a completely different type of function, we're dealing with a trig function, we still work with what we're given with. We're still relating ideas with sine of x to what we've learned before, and we're able to find the limit. We just need to work with what we're given with and follow the steps, and we'll end up with the answer. So next time, what we're going to learn is we're going to learn differentiability and continuity of derivatives when the derivatives exist. And then after that, we're going to find faster ways for computing derivatives, since we don't want to do this all the time, right? We don't want to evaluate the limit each time for computing derivatives. So we're going to find faster ways to do that.